All right, so here's an exercise. And I'm actually, the first thing I'm going to do is I'm going to sort of rephrase this in terms that make a little more sense to me. So, so just as a reminder, x is a function from the space omega, which is endowed with the sigma algebra F, and it maps to the space S, which has the sigma algebra fancy S, which is just these two are the same thing. I just need some way to differentiate a capital S from a fancy S, and so I just use a cursive S. Okay, so we must prove that if the sigma algebra generated by A is S, then the so sigma of x. So here, so we want to prove that x inverse of A generates sigma of x. So that means that the sigma algebra generated by x inverse A is equal to sigma of x. So the sigma algebra generated by x inverse of A equals x inverse of S, which is, this is, I sort of like this notation better, using this x inverse of a collection of sets to mean the collection of inverse images of subsets, or inverse images of sets in cursive S under the map X. And this is sort of like, let's see here. So I learned measure theory from following Fallen's textbook. I have a whole bunch of Fallen exercises on this channel. So in general, I'm going to favor that sort of notation. And so this is sort of the notation that you'd see in Fallen. You'd see a lot of like X inverse instead of like the set X in B where B belongs to S. And then also, I'm not familiar with this sigma of x notation. And I think that I sort of like x inverse of s better because there's more information given in the notation. Here, x inverse of s tells you, okay, so we have a function x and we have a set s or a collection s that we're pulling back under this map x. Whereas if you're just given sigma of x, you're not told what the collection S is. So I think this notation gives you a little more information. Anyways, so this is what we're trying to prove. These are two sets, and we want to prove that they're equal, so we're going to prove by inclusion. So this direction, let's see here, am I doing this correctly? Yeah, this is straightforward, because let's see here, if sigma of A generates S, or sigma A equals S, certainly A has to be contained in S, and then this inclusion is preserved under pullbacks, because anything of the form x inverse A, where A is an element of fancy A, well, any such set A is also an element of fancy S, and so it will belong to x inverse fancy S, and so therefore x inverse fancy A is contained in x inverse fancy S. And now this implies, what happens if we consider the sigma algebras generated by both of these sets? Well, we have sigma of x inverse A is contained in, again, the inclusion holds. The inclusion is preserved when you take the sigma algebra generation operation. But if we look at x inverse of S, this is actually, so sigma of x inverse of x is, or sigma of x inverse of S is precisely x inverse of S, because x inverse of S is a sigma algebra. So I guess that's sort of a separate lemma. I don't remember if it's mentioned in the book, but the sigma algebra generated by a sigma algebra is just itself. And I guess that's straightforward because it's x. So if you have a sigma algebra S, or let's see, is there a letter we're not using here? Let's say C. We're not using the letter C. So let's suppose C is a sigma algebra. Then the sigma algebra generated by C is the intersection of all sigma algebras which contain C. And certainly this intersection, so any element that's any sigma algebra over which you're taking this intersection will contain C. But furthermore, C is one of these sigma algebras because C contains itself and it is a sigma algebra. And so the intersection of all such sigma algebras is just going to be C itself. And so if you take sigma of a sigma algebra, you just end up back with yourself, or with itself. So yeah. I guess in that sense it is sort of like a projection operator, because if you take sigma algebra of something, you get sigma algebra, then if you take it again, you're just back where you started. Anyways, okay, so this completes one inclusion. So now we want the other inclusion. So for this inclusion, we need a lemma. And I don't know if this lemma is necessary for this exercise. This isn't used in Durrett's, if that's how you pronounce it, in his solution manual. But I wasn't really... There were some things in his solution that were a little bit... It wasn't clear to me how to rigorously prove them. And so instead I took a different route. And this is a... fact... Let's see here, I had to do some looking online. I actually ended up going to ProofWiki to finish this exercise and come up with this idea. But this is actually a lemma this is a theorem in Folland. So you can go to that textbook and read it if you want. So let f be a function from a measurable space X with a sigma algebra M to measurable space Y, comma N. And let cursive E be a, and this is of course notation from Folland, he likes this for a generating set. Let E be a subset of N which generates N. Then F is, and I'll write Mn measurable. So this means that f is a measurable function from the sigma algebra M to the sigma algebra N, meaning you take the inverse of any set in fancy N under the function f, and that will give you a set in fancy M. So this holds if and only if f inverse of script E is contained in M. So this is basically saying, so this is sort of like saying that f is measurable from M to E. Except that I think measurability is defined only for sigma algebras, and E need not be a sigma algebra. So anyways, let's prove this lemma. Okay, so since E is contained in N, this direction is trivial. Because if the inverse image of any set in N is in M, then certainly the inverse image of any set in E is in M, because any set which is in E is also in N. Okay, so that's one direction of the if and only if statement. So for the other direction, we're going to define N prime to be the collection of all elements in fancy N, such that if you pull them back into X, you end up with an element in M. Certainly, E is contained in n prime because for this direction we're assuming that f inverse of E is in M, which means that every set in E satisfies the condition for being in n prime. Since n prime is a sigma algebra, M is. No. Since M is a sigma algebra, n prime is. And this is something that, again, I don't know if this has been proven, but if you take the inverse image of a sigma algebra... No. Why is this true? Okay, so basically the reason that this is going to hold is that if you n prime is going to be closed under all of the inverse image, under all of the requirements for a sigma algebra, because all the requirements for a sigma algebra work really nicely with inverse images. You see, in inverse images, when you're talking about like functions, inverse images are not nice because they might not exist. You might not have a function which is one-to-one or onto, so it might not be nice. However, when you're talking about sets, inverse images are actually really nice because inverse images preserve a lot of set operations. Namely here, inverse images preserve complements and unions. So basically what's going to happen is that if you have a collection of sets in n prime and you take their union, like a countable union, then f inverse of the countable union will be the union of the inverses. And since all of these things will be in M, and since M is a sigma algebra, the resulting thing will be the resulting set will be an element of M. And similarly for complements. And so that's why we sort of deal with that's sort of why sigma algebras work really nicely, and like with the measurable function definition we are considering inverse images, because these set operations work really nicely with inverse images. But anyways, so you can prove that n prime is a sigma algebra. So n, which is the sigma algebra generated by E, is contained in the sigma algebra generated by n prime, because E is contained in n prime. But n prime is a sigma algebra, so this is precisely n prime. So thus, any element of n is in n prime, which means precisely n prime equals n, because n prime is a subset of n. Which confirms that f is m n measurable. Because the fact that any element of n is an n prime means that any element of n is such that its inverse image under f is in M, which is what it means to be measurable from M to n. Okay, and we sort of use this lemma in an interesting way in this proof. So, returning to the proof of this inclusion in the statement that we're trying to prove for this exercise, note that x inverse of A is contained in sigma of x inverse of A. And why is this true? This is true because, well, It's just any set is contained in the sigma algebra generated by it. So this is sort of trivially true. So now, by our lemma, basically what we are doing is we're applying our lemma. This tells us that the inverse image, this tells us, so x inverse of A is contained in sigma of x inverse of A. So in our lemma, we're using A in place of E, and we're using sigma of x inverse of A in place of M. So what does the lemma tell us going backwards? Since sigma of A is S, we use S in place of N in this theorem, or in the lemma. And so X is measurable from where? So it's measurable from M to N. So M in this case is this entire thing, sigma of x inverse of A. And what is N in this case? Well, I just said it's sigma of A, which is, of course, S. So since sigma of A equals S, we conclude, so the inverse image of any element of S is an element of sigma of x inverse A. That's what it means to be measurable in this sense that I've just written. So what we conclude is that x inverse of S, this is just writing what I just said differently, is contained in x inverse of A. And that's the inclusion that we wanted, and hence equality holds. Of course, I say it's the inclusion that we wanted. It's in the different direction from what I wrote before because I wrote the sets in the opposite direction for no particular reason. But yeah, this proves the equality of the two sets in question. So this is sort of I like this proof. It is let's see here. So I was looking on Stack Exchange as well. This is considered more of a top-down approach because all we're dealing with is sigma algebras generated by collections. And so we're not really dealing with the sigma algebras directly. Whereas the first thing that I was thinking of was to sort of do what's considered more of a bottom-up approach. And so here's what I was thinking for that. If you think about, so the one direction, the first direction that we proved, that sigma of x inverse A is contained in x inverse of S, that's always straightforward. But to prove that x inverse of S is contained in sigma of x inverse of A, basically, the idea was consider an element of S and try to imagine how it would be constructed from A. And it turns out, given a collection A, and the sigma algebra S generated from A, there's a way to characterize elements in S in terms of elements in A. And it basically answers the question of how could you construct an element of S from elements of A. And so the idea is, you know that this set S has to contain A, and it needs to be closed under complements and countable unions. So what you do is you allow for all sets in A, then you allow for all complements of sets in A, then you allow for countable unions of sets in A and their complements, and then you allow for complements of these countable unions, and then you end up with another set that you're able to take unions of, and then you end up with another set that you're able to take complements of. And so as long as there's only finitely many times that you're taking complement, or as long as this procedure stops after a finite number of steps, you're in the sigma algebra. And so, of course, as it might be clear from how I've described it, but this is pretty messy. I think it uses transfinite induction. But it would work because basically the idea is what you would do is you would say, okay, so let's say we have a set in X inverse of S. So it's a set of the form X inverse S, where S is an element of fancy S. Now we think, how could we possibly construct S from elements in fancy A? And we suppose that we have some formula which tells us how to construct S from fancy A. And we know that such a formula exists because of the process that I just described. Okay, so having written S in terms of elements of A, the only operations you apply to elements of A to obtain S are complements and unions. And these are things which are preserved under inverse images. So what you do is you take this thing, you take this element of S, you take this element S, you break it up into how it's constructed in A, and then you take the inverse image of this entire formula, and when you take the inverse image of the entire formula, you're able to construct this, or you're able to bring the X inverse inside all of the set operations, because set operations behave nicely with inverse images. And then what you end up with is you end up with some formula involving complements and unions of elements of X inverse of A. And so the set that you end up with is a set in the sigma algebra generated by X inverse of A. And so that shows you that any element in X inverse of S is actually also in sigma of X inverse of A. And that's how you prove this direction. So of course, as you can tell by how long it took me to describe it, it's a longer, more detailed proof. But I do also sort of like it because it's sort of more hands-on, and it actually gives you a procedure for given a set in, or given an element of one set, how do you sort of move it, or not really move it, but how do you deconstruct in a way that shows clearly that it's contained in the other set. But anyways, yeah, we finished this exercise a while ago, and so we are done.